Hello, Trinity Tigers. Welcome to the Learning Together live webinar series, part of a lifelong learning initiatives presented by the Trinity University Office of Alumni Relations. I am James Sanders, class of 1998. I am your incoming president of the Trinity University Alumni Association, and it is my pleasure to introduce today's webinar speaker, Dr. Dennis Ugolini, who's the professor and chair of Trinity's Department of Physics and Astronomy. He's going to give a presentation today on expanding the search for gravitational waves. Through funding from the National Science Foundation, Dr. Ugolini and 10 former and current students have worked on improving the sensitivity of the interferometers, helping them see further out into the universe. Today we will learn from Professor Ugolini's presentation what gravitational waves are and what can be learned by studying them, how the Advanced Laser Interferometer Gravitational Wave Observatory detects gravitational waves. Also, we'll learn details of 3 detections of gravitational waves from merging black holes made so far, and the future of gravitational wave astronomy. Please know that you'll be able to submit your questions, and as you listen to Dr. Ugolini, he'll be happy to answer those following the presentation. So, ladies and gentlemen, Dr. Ugolini.
Thank you, James. So, hello, thanks for having me today. I've been at Trinity since 2003, and I've been a part of the project I'm going to talk to you about today since 1999. And for 16 years, I used to give talks that said, someday, maybe we will be able to detect the curvature of space itself. But within the last 2 years, that's actually been accomplished. And so very happy to be able to give talks now where we have a working instrument and to introduce you to the dawn of an entirely new type of astronomy, which will be gravitational wave astronomy. So that's what we're going to start talking about now. And the first thing I want to do is talk about some of the misconceptions I think a lot of people have about how gravity works. And the first one is that gravity affects mass. The heavier something is, the stronger the pull of gravity that it feels. Newton's second law, force is mass times acceleration. It turns out that gravity will actually affect even massless things. Even light will be affected by the pull of gravity. And here is some experimental proof. Imagine if you had a galaxy, a very dense object, and then behind it, out of our field of vision, is an extremely bright object, like a quasar. Light is going to come off of that object in all directions, but as it passes around the dense galaxy, the light's path is going to be bent by the pull of gravity. The camera on the right is supposed to represent us. And the way your brain works is whatever direction light came from last, you interpret as it had always come from that direction. So light that bends in from above, you're going to think came from above the galaxy. Light that bends in from below, you're going to think came from below. And so when we look at the galaxy, pictured on the left, you see 4 bright images and a cross around it. Those are all actually images of the same object, and the object is behind the galaxy. It's not in any of those 4 spots. So this is a demonstration of how light itself can be pulled by gravity. A better way to think of gravity is Einstein's picture from general relativity, that gravity is a distortion of space such that straight lines aren't straight anymore. Imagine if you had a large elastic sheet like a trampoline, and you were to roll a marble across it. It would travel in a nice straight line. But put a heavy bowling ball in the center of that trampoline, and now the space itself curves around where the bowling ball is. If you were to roll a marble by, it's going to naturally want to follow that curve, and it's going to look like it's orbiting the bowling ball. Now, another consequence of this is we picture gravity as being instantaneous. If a heavy object appears in a certain spot, everything should adapt and start feeling the pull of gravity from it. But that turns out not to be true. There is an ultimate speed limit in general relativity, the speed of light. So any change you make, the gravitational effect is going to radiate outward. So going back to our trampoline example, imagine you took that bowling ball and you kind of moved it around in a circle at the center of the trampoline. As it moves, the trampoline is going to curve down when it's near and then snap back up when it's far. But the whole thing won't instantaneously show that effect. This up and down curvature is going to radiate outward at some finite speed, and it's going to look like a wave. This is what we call a gravitational wave. It is a traveling change in the curvature of space itself. Now, all that is predicted by general relativity, but here is the funny part of that theory. Imagine you have two extraordinarily massive objects, black holes. They get too close to each other. They get caught in their mutual gravitational pulls, and they start spiraling around their mutual center of mass. As they do so, they're going to radiate gravitational waves. And that takes a lot of energy because space is very stiff, does not like to curve. As the system loses energy, the black holes collapse towards each other. And as they get closer, they start to spin around each other faster, much like a figure skater pulling their arms into their body. So you get waves that are increasing in frequency because as the black holes spin faster, the waves are crunched closer together. And also, as they get closer, they lose energy quicker, and so the waves get bigger. Now, eventually, those two black holes are going to crash into each other and merge into one larger black hole. And this is where the funny thing happens. General relativity predicts what will happen when those black holes collide, but the mathematics of it involves 16 different equations, the solution to each of which depends on the other 15. It's 16 simultaneous chicken and egg problems. It's not hard to solve. It's actually unsolvable. So we have a theory that tells us what would happen, but we can never actually get the information out of it. All we know by making certain approximations is that eventually it'll settle down into one bigger black hole. But here's what's exciting about gravitational waves. If I could detect the wave that comes off from the beginning of this event and the wave that comes off from the end of this event, then I know everything in between is what happens internally when these black holes merge. The idea is if I am in a sufficiently what we call strong field situation, enormous amounts of mass moving very quickly, then I can experimentally measure the parts of general relativity that we can't directly calculate. This doesn't just apply to black holes. It applies to other objects like supernovae. Supernovae are particularly exciting because the way we discover them now is 12 hours after the light reaches Earth, some dairy farmer will look up into the sky and say, there's a star there that wasn't there before, but now it's too late. The event has already occurred. But it turns out that the gravitational waves from the explosion of a star shoot straight out and come toward us at the speed of light. The light from the event also travels at the speed of light, but it starts from the center of the star and scatters from atom to atom for several hours before it escapes the outside of the explosion and can start traveling to Earth. So there's going to be a lag there. If you could detect gravitational waves and triangulate where they came from, you could tell the Hubble Space Telescope, look at this part of the sky and wait 6 hours. And then you'll catch a supernova from the very moment it begins. Dark matter, dark energy, the Big Bang itself, and who knows what other kind of objects that we haven't even thought of yet should all be able to generate gravitational waves. It's like inventing a new type of telescope, but instead of looking at radio waves or X-rays, we're looking at gravitation. And that allows us to see things like black holes that we couldn't see with light. So great, let's do it. Why haven't we done it already? Let's build this thing. Well, the problem is gravitational waves turn out to be very, very small. We measure them in terms of this quantity I've labeled a strain. It's a change in length per unit length. The more distance you measure, the bigger the effect of the curvature of space. But in 3 dimensions, when space curves, it will actually distort the distances between objects. So if the strain was, say, 0.01 or 1/100, then if you and I were standing 1 meter apart and one of these waves passed through, that means the distance between us would be changing by 1 part in 100 or 1 centimeter. That would be easy to measure. But now let's take a catastrophic astronomical event. I'm going to take 2 neutron stars, a little bigger than our sun in mass, a little smaller than a black hole. Each is about the size of San Antonio itself. And I'm going to say they're about to crash into each other. So they are orbiting around each other at about the radius of the 410 Loop Freeway around downtown San Antonio. I never feel like when I say that it gets the respect it deserves. I pretty much told you 2 sun-sized objects are inside San Antonio, spinning around on the freeway and about to collide. Now, this would be very, very bad if it happened near us. So I'm going to pretend that this event is happening not in our galaxy, but in the next cluster of galaxies away, which is about 60 million light years. And we can calculate by the time those stars collide, they will be orbiting each other about 400 times a second. If I put all those numbers together, the number that I get out for the size of the wave that this will generate is 1 part in 1 followed by 21 zeros, which is not a real easy number to get your head around. The best analogy that I've been able to come up with is that this is equivalent to the distance between the Earth and the Sun vibrating back and forth by the width of a single atom. And this is a huge signal. This is one of the largest signals we can conceive of. It turns out you can't generate them on Earth to be big enough because there's just not enough mass to move around. We just have to wait for the universe to cooperate and generate an event of this size. We also have to find a way to measure such a tiny, tiny effect. Well, it turns out there is such a device. It's called an interferometer. And the name comes from the fact that we are measuring things by interfering, in this case, beams of light together. We're taking advantage of the fact that light is a wave. So I take light that has one specific wavelength, in this case, a laser. I'm going to send it into a series of optics and mirrors that split it into 2 beams of light, which travel off in 2 different directions. I have them travel as far as I possibly can, because again, the more space I measure, the bigger the effect. So the 2 beams, which are going up and to the right in the picture you're seeing, are traveling as far as the curvature of the Earth will allow. And then they are going to bounce back and forth between 2 mirrors several hundred times. But eventually the 2 beams will leak back out and they will recombine and head downwards toward the light sensor, the photodiode labeled PD at the bottom. And when this happens, how far the beams traveled will depend on what kind of phase relationship they have when they arrive. If they travel the same distance, then when they come back, they'll both be in phase. They will rise and fall at the same time. And then they will add together and give you lots of light. But if one travels a little farther than the other, then it might be rising when the other falls and vice versa. And when they superimpose on each other, they will actually cancel out and you will get no light. It turns out if you can tell the difference between lots of light and no light to 1 part in a billion or better, you will have the sensitivity to measure the waves that we're looking for. And that is something that has actually been built. It's called the LIGO Project, where LIGO stands for Laser Interferometer Gravitational Wave Observatory. I guess because LIGO didn't sound as good. There are 2 such observatories. There's one in southeast Washington State in an area called the Hanford Nuclear Reservation. There is one in Louisiana, just east of Baton Rouge, in an area called Livingston. You want to have multiple observatories because they are so sensitive to any kind of vibration that you want to be sure the signal you measured is not a car driving by or an earthquake somewhere within 1,000 miles. By having 2 signals in such vastly separate areas, both show up with the same shape at the same time, plus or minus the travel time of light, you are more convinced that it had an astronomical origin. So these 2 observatories, they're largely run by Caltech and MIT, but there are dozens of institutions and over 900 scientists, astronomers, engineers that participate in building, operating, and analyzing the data from these observatories. And they are entirely funded by the US National Science Foundation. This is a slide that I am required to show as part of the LIGO scientific collaboration, but I like doing so for 2 reasons. One, it gives you a real sense of the global nature of this collaboration. If you look around this slide, you'll see institutions from the United States, but also all parts of the United Kingdom, Australia, Spain, Japan, Brazil, China, etc. The other thing I like about it is I did not make this slide. This is supplied to all members of the collaboration. So I have no idea why Trinity University is the very first institution listed at the top left. I'm not going to argue with it. I think it's great. I have just no idea how that happened. Maybe it just looks best. I don't know. But here are the observatories. Again, we make them as large as the curvature of the Earth will allow, which in this case is 4 kilometers, which is just under 2.5 miles. So those arms are concrete tunnels going off in 2 perpendicular directions, 2.5 miles down to the end, where there's just a chamber with a mirror in it to bounce the beam back. You can easily see these laboratories from the air. And again, the one on the left is in Washington State, the one on the right is in Louisiana, and you can tell that because it's half underwater. This is a kind of the most complicated graph I'm hopefully going to show you today, but this gives you a sense of how sensitive the device is and some of the challenges we have to deal with. So let me describe this in detail. The bottom of the graph is the frequency of the gravitational wave you're trying to measure. And you'll notice that it starts at 10 hertz. A hertz is a cycle per second. So 10 waves per second up to several thousand waves per second is where we are sensitive. Remember, that is the frequencies that black holes or neutron stars reached right before they collided with each other. So we will only see these in-spiral events right at the moment where collision and merger occurs. So these are going to be very short-lived events that we're looking for. The axis on the left shows you the strain of the wave, and the very top of the graph is that magical 1 part in 10 to the 21. So anywhere we're below that line is where we're sensitive. The LIGO laboratories were first built in 1999, and they finally achieved their design sensitivity in 2005. That's the green curve. It's limited on the left by the fact that the ground is shaking. We live on Earth, and Earth has seismic vibrations, and they are mostly at lower frequencies. That is what really prevents us from seeing these objects before they collide with each other. All the other spikes you see are a variety of problems. 60 hertz noise from wall power, vibrations of the atoms in the bulk of the mirrors themselves due to their thermal motions, and so on. There are hundreds of scientists, of which I am one, whose entire job is to try to beat back those noise sources and make the interferometer more sensitive. So we ran where the green curve is for 2 years, from 2005 to 2007, and then again from 2009 to 2010 it didn't see anything. Between 2010 and 2015, many technological improvements were made to move the sensitivity downward. That's where we are now, is the a little colorblind, I guess that's red, the red curve. The farther down you go, the more sensitive you are. So the red curve is where we are now, and then the blue curve below and the curve even below that are where we hope to get in the next couple years with consistent technological upgrades. But the red curve is important because this is where we were in September 2015. And at that time, there was a planned data-taking run of the interferometer. It was supposed to run from September 18th, 2015 to December 18th, 2015. I want you to keep those dates in mind, late September to late December. To get ready for the beginning of the September run, we had what was called an engineering run, starting September 11th, 1 week beforehand. The interferometers were brought up and put into science mode. In every way, it was like we were taking data normally, except if problems were found, the decision had been made that we would immediately shut everything off, fix the problems, and then bring it back up again. It was like a shakedown period. 2 days into that shakedown period, at 4:50 in the morning on Monday, September 14th, suddenly the absolutely perfect signal that you could ever want showed up in both detectors, one 7 milliseconds before the other. So the top graph on the left represents the Washington Observatory, and on the right is the Louisiana Observatory. And it is in every way the signal that I described to you. It's a wave that gets bigger as time goes on, and the wave fronts get clunched closer together as the two objects that generated it get moving closer together and spiraling faster and faster. You'll notice the two observatories look almost exactly the same as each other. The second set of graphs are a computer model using an approximation of the theory of general relativity that is the best fit for the objects that generated this kind of wave, which I'll talk about a bit more. But what's important here is if you take that model and subtract it from what we actually measured, you get that staticky looking curve underneath. This is the difference between, again, the model and what we measured. And what you'll notice is on the left, when nothing's happening, it's a certain size of static. And then as you go along, where more and more things happen, the size of the static doesn't get any bigger. What this is telling you is that you're not introducing any more noise because of a discrepancy between your model and the actual data. The model is a really, really good fit. It's one of the many reasons we're confident that we detected 2 actual black holes spitting into each other. But I think the best way to visualize it is at the bottom. The bottom axis is time. The vertical axis is the frequency of the wave. And then the color tells you how much power there was at that particular frequency, at that particular moment. And so you'll see this gentle curve sweeping upward in frequency and getting brighter as it goes, which means the wave is getting bigger and bigger. Our eyes are just much better at picking out that a real event occurred in this type of pictorial graph than in the ones above it. I want you to hear what the wave actually sounds like, because by the time they collide, when they're going several hundred cycles per second, that's an audio frequency. You can't actually hear it in space, but what we're going to play is if you took the signal from the interferometer and played it through a loudspeaker. So that's the file we're going to play right now. Hopefully. Now, what you probably heard was a lot of static, and if you were paying real close attention, you heard something right in the middle that sounded like a shoe dropping. Try that one more time. That thump was the most energetic event in the history of the universe since the Big Bang. Hard to perceive, though. So what we've done is we've taken all the frequencies and we've shifted them upward 400 hertz to fit more into the ear's sensitive range. So we're going to play that file now. And that little whoop, that sounds like a slide whistle in between, that is, again, the signal getting louder and higher in frequency. Again, much easier to detect with the ear than with the eye. Unfortunately, we can't tell precisely where the waves came from because you need a triangle to triangulate. And at the time, we only had 2 detectors running. So at best, we can tell it's coming from a stripe going across the sky. If you had more than 2 detectors, you could tell much more precisely where they originated. We'll get back to that later. Our model tells us what the size of the objects were, but you can also do some very basic math to figure out in terms of how many times the mass of our sun were these objects. And they turned out to be combined on the order of 70 times the mass of our sun. And from how fast they were orbiting each other when they collided, we can tell how far apart they were. And it turns out that right before collision, they were roughly as far apart as San Antonio is from Waco. This is how we know they're black holes. There's no other known object in the universe that would both be that massive and that small, such that they could get that close together before they collided. So from doing all this data analysis, we could put together a picture of what happened. Approximately 1.3 billion light years away, and therefore 1.3 billion years ago, 2 black holes, 36 and 29 times the mass of our sun, respectively, got too close to each other, started spiraling around, and eventually collided, forming one larger black hole that was 62 times the mass of our sun. Eagle-eyed viewers will notice that 36 plus 29 does not equal 62, it equals 65. The 3 solar masses of mass that are missing were all converted into energy in the 2,000ths of a second that this event occurred. That is where the gravitational waves come from. If you were to take the energy emitted during this event, it is greater than all the other sources of energy in the entire universe combined times 50. That's how catastrophic an event this would have been. Now, since then, we've noticed 2 others. Remember I said the run was originally supposed to end December 18th. At the time it was decided, especially since we knew we had seen something, well, no one's going to touch it over Christmas. So let's just keep it running for a while longer. And the run was extended. And sure enough, on Christmas Day, or the next day in Europe, another event occurred. It's much harder to see by the naked eye, but it was longer in time. And so it was easier for our software to pick it out of the noise. What was particularly interesting about this event is we can say with some certainty that one of the black holes was rotating about its own axis before it collided with the other, which gives the sense that it itself may have been the result of a previous merger. Then a second science run was begun very late in 2016 and just concluded last month. That generated the event you see on the right in January of this year. What was special about this event is, once again, it was very large, easy enough to see with the naked eye. And the other thing is it was more than twice as far away. It was nearly 3 billion light years. The entire universe is only about, we think, 14 billion years old. So we're spanning across more than 20% of the radius of the entire universe at this point. So why is this interesting? I find this graph to be one of the best explanations. This is a picture of all the black holes we know of, sort of. The ones in the lower left corner are all the ones we've detected by X-ray telescopes. And you'll notice that they're kind of small. The smallest mass that will generate a black hole is about 3 times the mass of our sun. And most of the ones we've found with X-rays are that small, because most of them should be that small. You should get fewer and fewer as the masses get bigger. There are also likely black holes at the centers of galaxies, but those are tens of thousands times the mass of our sun, so those don't appear on this graph. The 3 events, and also one detection that was not quite certain enough for us to label it as such, that's the one with the dotted line. You'll notice that those are all much bigger black holes. They're in a range astronomers call intermediate mass black holes. And I didn't fully appreciate until it happened how much this would throw astronomers for a loop. Because there are many models of the creation of our universe, of cosmology, that simply do not allow for enough intermediate black holes for 2 of them to ever simply bump into each other and merge and form even bigger ones. So the fact that we've seen this not once but several times means those models are simply wrong and have to be revisited. So this isn't the end. This is the beginning. We are at the dawn of a new field of astronomy here, and there's many more experiments coming online to participate. The farthest along is near Pisa, Italy. It's called Virgo, and it actually joined our science run during 2017. We're hoping maybe there will be results coming out of all 3 interferometers that will allow us to better triangulate where the event came from. There's one in Japan, there's one in Germany, and the US National Science Foundation is cooperating to build a new LIGO Observatory in India. Ground was broken for that this year, and we expect it to be completed by 2022. This is also not the only way you can detect these waves. Again, we're limited by the vibration of the ground in detecting things that go slower. So get rid of the ground. Why not put one of these interferometers in space? There is a planned experiment to do that called the Laser Interferometer Space Antenna. This is mostly a European project, probably scheduled for launch on the order of the mid-2020s. But that will be able to detect things with frequencies down to 10 to the -4th hertz, which, as you see here, are things on the orders of hours. It will be able to detect objects like black holes and neutron stars while they're still spiraling around each other, long before they actually collide. We even have ways we hope to see the supermassive black holes at the centers of galaxies, swallowing other objects or simply vibrating in place. That method is called pulsar timing. There are objects in the universe that give off very regular clock pulses, basically. They give off radio beamed signals that arrive on Earth at extremely regular time periods. They are a very precise clock. But if they pass through a gravitational wave on the way, since that's modifying the distance through which they've traveled, the arrival time is going to be affected. And so by integrating these pulsar signals from a variety of pulsars from all different directions for a long period of time, you can detect much, much slower waves still. So all these experiments are being revved up for the beginning of this new field of astronomy. If you're interested in learning more about it, LIGO has a magazine at the cleverly chosen website ligo.org/magazine with tremendous high-resolution pictures of the detector itself, some pictures of how we imagine these events look like, and so on. And if you're very adventurous and have some computer skills, every time we detect an event, a 1-hour block of real data in which the event is embedded is released at a website called the LIGO Open Science Center. And if you have some comfort with Python, you can go in and analyze the data yourself, or even if you're completely unfamiliar, there are tutorials on the website that can walk you through it. This is a great project for advanced high school classes who want to really get their hands on how this actual physics is done. That's the whole presentation I had. Happy to take your questions now. Thanks for listening today.
Great, that was fantastic. Our first question comes from Ryan, and Ryan asks, how can space bend? Isn't space the absence of matter, something that can be acted upon? And how can a nothing space be acted upon when there's nothing upon which to act?
Yeah, that's a good question. There's some historical basis for this question coming up too. As early as the 1860s, people knew of light as a wave, but then the question was, how can something wave if it has nothing to wave in, right? Sound requires air, water waves require water. But it turns out that space itself is the medium in which light is waving. We can then extend that farther. In the general relativity picture of the universe, when we say that space itself is distorting and that lengths are changing, well, light itself is the ruler that we use to measure those lengths. So when we say space is distorting, what we really mean is light is taking a different amount of time to travel from point A to point B. Space is not a thing that actually stretches and shrinks. It's just we have to kind of visualize it that way to get a feel for what's really happening.
Right. And I have a question. So the two centers, LIGO centers that we have in the United States, do you know how the sites were selected? Because it seems like Washington State being up kind of Pacific Northwest, a lot of seismic activity there. And then you said the other one in Louisiana is kind of potentially got some water issues at some point. Is that just available space, or are those problems that they're aware of? Or
well, yeah, those are surmountable problems.
Okay,
that's probably the best way to put it. The number one thing is the observatories have to be somewhere as isolated as possible. You don't want them anywhere near civilization, basically, because every time we walk, every time we drive our cars, every time we operate a machine, we are creating ground vibrations, which dwarfs the seismic vibration that our Earth experiences all the time. You also would like them to be in areas where there are lots of technical people living, so you can hire all the engineers and site operators that you need. The Washington site is nearly perfect because there's an area called the Hanford Nuclear Reservation. It is a 400 square mile area that is entirely devoted to the testing of new types of nuclear reactors by the US government. So there are a few reactor installations spread around, and then the rest of the area is entirely empty. So you have a strong technical base, and you have 400 square miles of nothingness. It's exactly what you want. Can't make as strong of a case for Livingston. Really, at that point, you want it to be far, because again, the farther apart the two observatories are, the more confident you are you're measuring an astronomical signal when they see the same thing. And
so were they constructed simultaneously, or one spot was selected and that kind of determined the spot for the second one?
They were both selected simultaneously. The Hanford Observatory had a 6-month lead in being built. The idea being lessons you learned there could be applied in Livingston, and then that would, you wouldn't have to invent the wheel twice, basically. But they were both up and operating about the same time.
Fantastic. Any other questions from our participants? Okay. Thank you so much, everyone, for attending this live webinar. Our next one will be scheduled for October 23rd at noon Central Time, and it will be a live conversation between poet-writer Naomi Shihab Nye, class of 1974, and of course, our Trinity icon, Professor of English, Colleen Grissom. Thank you very much. Have a At the last minute, Jeff asked, will there be additional sites allowed for triangulation? I'm assuming he means in the U.S.
It's like the fake encore for the fake ending for a rock band. Encore. There are no plans at the current time to put more in the U.S. The fact that we're able to put one in India is great because it's far, it's on the other side of the Earth, which allows you to, by the different orientations of the laboratory, allows you to tell more about the polarization of the wave. And that's pretty much consuming all the resources that we have to put these things together. One thing that people usually ask, and I'm surprised hasn't come up yet, is how much do these laboratories cost? The initial LIGO installations were $360 million spread over 10 years. I like to put this in context two ways. One is, as a former particle physicist myself, that's not much. The particle accelerator in Switzerland, CERN, and the experiments that they have running there are on the order of $8 billion. So this is budget compared to what big physics can be. The other way I like to phrase it is 1.4 Alex Rodriguez's, because it turned out to be the exact same 10-year span when he had his $252 million contract with the Texas Rangers. So It's a lot for astronomy. It's not so much for particle physics. And the return on investment is turning out to be fantastic. Right. But there's only so much you can get to build new observatories, and right now, and so much staffing power and brain power to build it, and all that's going into India right now.
Jeff had a follow-up to this question. So the other installations that are built, are they allowing for triangulation? Are they built yet, or? So the one that is built and running and sufficiently sensitive to be useful is Virgo in Italy. We have a data sharing agreement with them, so we can look at their data, they can look at ours, and so the triangulation can happen immediately. As more installations come online, possibly such arrangements will be made with them as well. It's a different field in that it benefits more from collaboration than competition. If we were all racing each other, then we would lose the ability to have these confidence checks and this triangulation, timing measurements of are the waves actually traveling at the speed of light, where by cooperating and having all the installations be as if one big observatory, we're able to do all these things. Right. Well, all the questions are starting to come in now. So Colin has submitted 2 questions. His first question is, gravitational waves are predicted by inflation theory, but what are the realistic prospects for detecting gravitational radiation from the Big Bang cosmic inflation, either by LIGO or another more sensitive detector? It is probably, theoretically, going to be much lower frequency. And so something like pulsar timing has the best shot. But we don't have, assured theoretical understanding of what we're expecting to see here. But most of the stochastic predictions I've seen say the lower frequency, the better. Okay. His second question is, although there's no reason to doubt it, but has the speed of light been confirmed as the speed of the waves themselves? In other words, is the speed of light the speed at which the waves propagates between the 2 LIGO sites? To a very limited extent, it's been confirmed in that it's not like half that, right? I mean, we expect the waves to arrive. The 2 installations, if you were to fire a light beam from one to the other, it should take 10 milliseconds to go from one to the other, down to the second decimal place purely by accident. It just worked out that it was a very round number like that. So first of all, the detections we've actually made have all been less than 10 milliseconds apart. So it's not grossly slower than the speed of light. Another thing we've done is you can take data from one installation today and data from the other installation from last Thursday, and you can compare them and see if you ever get matches that are extremely far apart, and you don't beyond what you would expect from just random chance. To get really sensitive measurements of this, again, the more installations, the better. So right now we don't have the sensitivity to say more than it has to be at least close to the speed of light, but your precision increases dramatically with the more observatories you get. Derek has a question. He says, you discussed as many as 4 black hole mergers on the chart in a relatively short period of time. Have there been others since? What type of frequency do you expect for these black hole mergers in the future?
So, 2 parts to that question. First of all, have we seen any since? The second science run ran from late November of 2016 to August of 2017. It has only just concluded. I presented one detection from there because that is the only one that has been publicly released. There is a significant lag time between when things are detected and when they are publicly announced. And there's 2 reasons for that. One is to make sure you're right, to do all the data analysis necessary to determine, was it a real detection, what direction did it come from, what kind of objects generated it. The second reason is that there are a lot of astronomers who do a lot of service to the collaboration to make the observatories work. For example, there's a whole group that just does calibration, making sure we understand the detector thoroughly enough that we know a signal this size means a strain this big. But those people also want to be analyzing the data to pull interesting astronomy out of it. So the delay between detection and announcement is to allow them to both perform their service to the interferometers, but also get value out of being in the collaboration by having first crack at that data to be able to do the astronomy. So have there been detections since January? The answer I am required to give is look for announcements from our spokesperson soon, right? There may have been, I literally can't tell you. As far as how common they are, again, with only 3 events, the error bars are pretty broad. The last time I looked at this number, it was expressed as there should be a black hole merger 9 to 240 times per year per box, 3 trillion light years on a side. So it's per cubic gigaparsec per year. And the entire universe is only about 15,000 of such boxes, so they're enormous boxes. In other words, they're rare events. And we're getting a better handle on how rare as we go along, but you shouldn't expect one in our galaxy anytime soon. And that's good, because we don't want that energetic of an event that close.
Sure. Well, thanks for all the questions that have come in. It looks like that concludes the questions. And so again, thank you everybody for attending, and we look forward to seeing you on October 23rd at noon.